Hello everyone, welcome back. Today I'm showing you the next bit of the little screen and memory thing I've created. So these monstrosities of circuits. Essentially this one here is an adder, a subtractor, a multiplier, or at least 90% of one. This here was my first try at a subtractor. Didn't turn out very good. As you can see, the signal just kind of dies out right around here, so oh well. So yeah, my goal with building these is to not actually what's it called? Not take someone else's design, build it all myself so I actually understand what's going on. For example, like this circuit here, yes, it's just copied up. I know what each part of it does. This is an AND gate. It essentially says if both of these are on, then it needs to output 1 at this level. So when both of these get turned on, this AND gate, as you can see, torches turn off, this torch turns on, which gives an output into the next level, which would then output over here. So yeah, my goal is just to build it all myself so that I actually understand how things work. So yeah, I'm just gonna give you a bit of a showcase. And yes, this time I'm actually recording audio. Sorry about last time. So, starting with one redstone lamp. This is our input, on or off. This can be, if you break that, it can be wired in with some other sort, or with some input that is automated. So you don't actually have to physically come over here and put an input, but this just works better for testing. So, now this is just how I designed it, but we need to first build our AND gate, which, as I said, will take the input if both inputs are on and give an output to the next level. So just a couple of repeaters here just to make sure signals don't get crossed. Redstone torches. So this here, now as you can see what's happening a bit easier, that turns on, it turns that portion on, or here. That'll be our output for this AND gate. It turns that torch off, but this redstone dust is still on because this is still on. So it forces it to have both of them on for this to turn on. So now let's, oh yeah, that's what I'm forgetting. I also need a couple slabs. There we go. So we need to wire this in. So that, yeah, this here is to stop the dust from connecting. And then this line here is just so that we can pull the signal out. So that there is now our input to the next line up, since as you can see it's just copied all the way up. So now we need an exclusive OR gate, or a gate that only activates when one of the inputs is active. So not when both are active, only when one. So as you can see here, the quick thing I did here. It's actually using the comparator's feature where it, in subtract mode, takes the input from the back and the input from the side and subtracts them, the back from the side. So when we turn one of them on, as you can see, there's a 14 input from the back and a 14 input from the side, so it outputs nothing. But as you can see over here, 13 from the back, 11 in the side. So it outputs. Now, if we turn on the other one, then it's 14 and 14, so nothing gets outputted. Little trick I learned just by messing around with the different components. So, this circuit here, this is a half adder. Essentially, it can take any two binary numbers, or binary inputs, and add them together. But where does this come in, this line here? Well, it would have to be inputted into the next one, which means we need 3 inputs, right? So here's the thing about that. Half adder, we need to double this circuit. So we need to run this into get that there, into another adder, or half adder. So I'm just building up the AND gate here, the exclusive OR here. That there. Those there. That bends around there and there. That goes there. So I hope you can follow along with what I'm doing. Essentially, I just copied this circuit here over to here. Now let's put the torch here now. This is just how I'm building it. Makes it easy for me to, or not exactly easy, but makes it fairly simple for me to just come along like this and pull the circuit out. Yeah, right here. One more block. I'm just doing this so that you can see exactly how I built it. This needs to come down, or from this block down 1, or from this block down 2, over 3, so that it gets beside this. Now don't worry, it's actually going to be sitting right in here, like this. It's going to be nestled in like this. So this would be the next layer up. So that's why it just has to come out, around, and then back through, so that it misses all of these blocks here and doesn't interfere with the circuit. Then all we need to do is bring this over here and yeah, up. So let's see, how far out did I bring it over here? Clearance of 1 block, got it. There, up, up, oh, up. Then over to here, up a block using a slab. Connect it in with redstone. Now this bottom layer here is slightly too long for the redstone to normally connect, so you will have to, somewhere in here, add a repeater. It's pretty simple, nothing that complex about it. Now, if we just add one of these here, that's too high, isn't it? I'm getting myself confused. What did I do over here? Oh, okay. This is why I was getting myself confused. Throw that there. Put a slab there. So now the signal, we have input 1. As you can see, it has given an output over here. We can determine that with the redstone lamp. Input 2. Well, 1 plus 1, that equals 2. 1 bit, or 1 binary bit, cannot input, or cannot show 2, because it can only show 0 or 1. 2 would be the next one up. Then it would be 4, 8, 16. If you're watching this video, I'm guessing you know how binary works, but that's a little tutorial, I guess. And as you can see, this AND gate has turned on, comes over here, and activates this part over here. No, this needs to be a slab. And then this would run directly into this repeater, which is this repeater here. So this block here is that block there. This would run into our AND gate up here. 2, 4. Bring it back a block there. That goes there. Stone dust. Now, I'm pretty sure you're wondering exactly how this works. If not, I'm going to tell you anyway. Essentially, I explained the comparators part. This block here is essentially, like, you could have it like this. It still technically works. Here, it'll be easier if I don't have this input here, if I have an input over here to show you, since it's actually using the right comparator. See, it still technically works, but that uses a block and a redstone instead of just using one block. And this here, since it's 2, could technically carry out farther. You don't need the repeater there. So, now that we have this, I'm just going to quickly turn these off so that it's not creating any redstone torch burnout clocks when I don't want it to. This needs a redstone dust. This is going into the first exclusive ore. If I remember to while editing, which I should now that I've said it, because I will hear it when I'm editing, I will show you the different, or at least, what's it called? The gates that I'm using are in a system called Boolean algebra, which is essentially binary algebra. Or it's not algebra, I guess. It's the logic computers run off of. So I'll show you the different gates in there. As I'm sure you've noticed, I've been using different color wool here. Actually, I'm sure you noticed. Green, blue, orange, white. So it just helps me determine what is what. Like pink here, all pink does is block signals from going through like this. So it just does that. Gray is the circuit that is, or like, it is the adding circuit or subtracting or multiplying. I got too lazy to change the color. But yeah, now this should work. As you can see, we have 2 bits now of input. So our output can be, this would be 2 plus 1, so our output can be 3. So let's say 2 plus 2, that wouldn't work, at least not here. Our output, if I remembered to add the torch, or the torch is up here. Yeah, sorry, I forgot about that. Would be 4. And this here is the same as this torch, it's just wired into the next one up. I just haven't built that. I just built the second layer here to demonstrate it for you. So yeah, say we did 2 plus 1, that's 3. Now, here's a quick question for you all. Do you think this circuit down here will send a signal up to this circuit? Go ahead and answer that in the comments real quick. Just from this signal layout. No, it does not, because you have an input of 1, and 1 is less than 2, which this would be. Therefore, this does not go up here. And it outputs 3, 1 from each individual circuit. The input comes in here, goes through this exclusive OR, realizes only one of them are on, gives an output, this exclusive OR realizes only one is on, and out. Now, if I flip this redstone lamp, what do you think would happen? It outputs 4 right here, because it gave 2 inputs, which means this AND gate turned on, because both of them are 1, or true, in Boolean algebra, activating this circuit, going into this AND gate of the second full adder, and turning it on. So this circuit here, that I've just showed you how to create, is a 2-bit full add, or a 2-bit adder. Pretty simple, right? Yeah, that's good. Okay, so let's look at this subtractor now, and tell me if you notice any similarities in these 2 circuits. Okay, as I start building them. So, I'm sure you've noticed one similarity by now, and that similarity would be that it's the exact same circuit, except that there's no redstone torch here. Now, I'll show you why that is in a second here, once I've built up the circuit. There. This actually needs to be a lamp. There we go. So, now that I've finished the circuit, it's just AND gate, exclusive OR, and exclusive OR. Pretty simple. So, we turn this one on. Okay, this would be our this is our first number. So, if we, here, let's just build it out. Let's say you have 1 minus 0. That would be the same thing as turning this one on. So this here represents your top number. Your bottom number is represented by this one. So, as we can see, our output, 1. Now, let's say we have 0 minus 1. Now, we can't exactly do that. Now, can we? Like this, technically we can, it's just some weird, or it's not a weird negative number, it's -1. And in binary, it's somewhat difficult to show that. I mean, over here, that is taking that concept into effect, where I was giving our input. So our input, our negative input is here. Now, if we were turning this one on, it was saying our output needs to be 1, and we need to give a negative signal, because it's 0 minus 1. So it would be -1. And then this negative would transfer into the next circuit, saying this is a negative as well. Okay, then it just continues on. Now, say we were to give a positive signal here. Okay, it goes through. It's just a whole bunch of exclusive ORs wired together. And then it gets here. So, a negative wired in. So if this is now negative, this is positive. They cancel each other. No output is given. So, we should see that it just continues to follow through here. Now, up here, I think I did my wiring incorrect. So, instead of this just following through, yeah, I did my wiring incorrect. Right now, a positive signal here is showing a negative output. That's why it's going through like this. But you can see, at least for the bottom bit here, it is canceling. Now, back to the smaller subtractor I built here. It's also much more efficient. It's a bit more difficult to do that. So, if we say turn this one on, this AND gate, which is saying this is essentially our negative, saying the next bit needs to be checked if it's true or false, on or off, and if it is on, negate it. It's saying don't do that, because redstone torch is powering it. So where was I? Sorry, my sister was trying to talk to me there. It goes through, keeps everything on, and gives an output. Now if we say negative, it still gives an output of 1, but it's also saying it's negative, which means you need to subtract from the top. This is essentially saying you need to borrow something to get this to be a 1. So, it's essentially an adder with half the input inverted. Last circuit I've built. It's a multiplier circuit. You enter, say, 3 here, and it's not quite finished. But anyway, essentially it's an adder circuit here, hooked up with a tower here that will, when you pulse it, activate all of them, taking your signal, letting it through, and storing it in its memory. Then that memory is fed back into the input, and you essentially just multiplied by 2. You had this number, toggle it once, the number gets put into here, adder goes through, does the addition, and now you started with 3, now you have 6, multiplied by 2. Now if we toggle it again, we get 9. 1 plus 8 is 9. Then to reset it, pretty simple. Just deactivate these and let the signal drain. And now they're deactive. So I'm not going to build out how I did it. Essentially, it's just copying the the adder and adding a memory circuit to it, or memory cell. So this is, or what this would be a repeated adder turn for a multiplier. Now, the multiplier that I've learned about recently would take some sort of input, like this. This is your first number, this is your second number. This second number would essentially be how many times you pulsed the repeated adder. And then it would do something really special that I've learned about. So here's our little equal sign, and then it would do something like this. Like, it would take this first number, and then look at this. If this was a 1, it would paste it down here, like this. Then it would take this number and look at this number. Since it's a 0, it wouldn't paste the first number, but it would add 1 0 to it. So it would look like this. Now, I haven't added this 0 in here just because 0 means false. No input is false, or at least binary. So it's just simpler, less work for me. Okay, so you can see what's happened here, right? It takes, if it's a 1, it takes the number, puts it in. Then it goes to the next. And then if it's a 1, takes the number, puts it in. And since this is the second digit in this bottom number, it would leave 1 gap here. Third number is a 0. Outputs are 0. And then the fourth number here, it's a 1. So what do you think the output would be? I'll give you a couple of seconds to guess. If you had guessed the output would be 1001 or 9, if you convert it to base 10, which which most people know as the only numbers or whatever, then you would be correct. So you can see essentially what it's done here. This is how computers nowadays would essentially do it. It would take the input here, the first number, and that would be the number that it lays out here, and then it would take the second number. If it's true, it would lay out the number. If it's not, then it doesn't. So, now, what do you think the final step of this problem is? Go ahead, guess. Well, we have a whole bunch of numbers that has been somewhat multiplied. Now all we need to do is take those numbers and add them. So yeah, it's pretty simple if you think about it. I have no idea yet how I'm going to implement it in Redstone, but essentially take your first number, look at your second number, if it's true, okay, lay it out, move over one. Take your first number, look at your second number, if it's true, lay it out, move over one. So it just repeats that. Once you've hit the end of your first number here, you just need to add them, which technically you can do the entire time. You can constantly be adding, since that's what this circuit would do. As soon as you have that first, or that's what my adder would do, as soon as you have this first one, it would give you an output, and then once you added more on, it would just keep giving you a different output each time. But yeah, so this is multiplication of binary bits. Now, here's a quick bit of binary trivia for you. So, how many bits is in a byte?